Let's talk about polar curves. In this video, we're going to talk about the formulas for the area contained within a curve and the arc length. So we have our two formulas at the top of the page here. For the area contained within a polar curve, we're going to have a definite integral with respect to theta. So I have alpha and beta. These are my two theta values. And then the formula for the integrand, you can see it as 1/2 r squared. This will be the area for a specific curve though. So r is f of theta as like a given function. So you might also see this with an f of theta in that spot. For arc length, we again have a definite integral with respect to theta. So I have the first and last theta values. And then square root of f of theta squared plus f prime of theta squared. And again, we're using r equals f of theta for the formula of the curve. So f of theta is r, f prime of theta is r prime. Okay, so we these formulas memorized, we can do things like the following example. So the curve we're going to think about is r equals cosine theta, and we'll compute the area contained within it and the length of the curve itself. So we're not given any particular start and stop theta values here because this is the type of polar curve that kind of traces out a finite path and then retraces it over and over as theta increases. So this is an example that we've done in class, but if you don't remember what it looks like, all you need to do is a quick theta r chart, plug in a few theta values. Compute their r values. So cosine of 0 is 1, root 2 over 2. Okay, and then we'll plot a quick image. Okay, this is a little bit off, but that's okay. It'll be enough. Okay, so when theta is 0, the radius is 1, so that puts me right at the xy point 1, 0. When theta is pi over 4, we're at root 2 over 2, which is something a little bit less than 1, right? We're going to be maybe out here somewhere. When theta is pi over 2, so we're on the positive y-axis, the radius shrinks down to 0. So we've kind of gone like this as we rotate. When we're at 3 pi over 4, we're facing this way, but the radius is negative, so we end up plotting kind of back over here. And then finally, when we're at pi, so facing this way, our radius is -1, so we bounce back and land right where we started. So in 0 to pi rotation, we've actually plotted the full circle here. So when we're talking about the area contained and the length, it's the area of the circle, the circumference of the circle, which of course we have geometry formulas to double check with, but this will be a nice example of putting these formulas in action. Okay, so let's do the area first. All right, so because 0 to pi traces out this circle exactly once, 0 to pi will be my bounds of integration. And then I'll have 1/2 f of theta, so that's the cosine theta formula that we were using, squared d theta. Right, and we have a memorized antiderivative for cosine squared. So I'll carry down this 1/2. Cosine squared is 1/2 theta plus sine cosine. And we're evaluating from 0 to pi. All right, so this is 1/4 pi plus sine of pi will be 0, so that zeroes that out. And then when we plug in 0, theta is 0 here, and then sine of 0 is also 0, so this whole thing zeroes out, and we get pi over 4. So that would be the area contained within that circle, which is also what you would get if you checked it with geometry. It'd be pi r squared with the radius of this circle being 1/2. If we wanted to compute the arc length, so the actual distance traveled tracing out that circle exactly once, we would use our other formula. Again, I want to integrate 0 to pi because those are the theta values that trace this circle out exactly one time. And my formula is square root of f of theta squared plus f prime of theta squared d theta. And this one simplifies down really nicely. So inside this integral, I have cosine squared plus sine squared, which of course add to 1. Square root of 1 is just 1. So this comes out to exactly pi. And again, because I chose a graph that was a perfect circle, we could check that this is the circumference of a circle with radius 1/2. But this formula will work in other examples where we don't have a backup option.